Hey there, it's Shannon Math Chick Myers, and today we are covering section 8.2.2 in the ZIL Intro to Differential Equations text, where we will be looking at how to solve homogeneous systems where there are repeated eigenvalues. So let's check it out. In general, if m is a positive integer and lambda minus lambda 1 raised to the m is a factor of the characteristic equation while quantity lambda minus lambda 1 to the m plus 1 is not a factor, then lambda 1 is said to be an eigenvalue of multiplicity m. For some n by n matrices, capital A, so remember capital letters mean matrices or column vectors, it may be possible to find m linearly independent eigenvectors, capital K1, K2, all the way down to Km, corresponding to an eigenvalue lambda 1 of multiplicity m, which is less than or equal to n. In this case, the general solution of the system contains the linear combination C1 times capital K1 e to the lambda 1t plus C2 capital K2 e to the lambda 1t, and then you would just keep going until you got to Cm capital K sub m e to the lambda 1t. Cool? All right. If there is only one eigenvector corresponding to the eigenvalue lambda 1 of multiplicity m, then m linearly independent solutions of the form capital X1 equal to capital K11 e to the lambda 1t, and then you'd get the next line would be capital X2, a solution vector, equal to capital K sub 21 times t e to the lambda 1t, and then you'd still have your capital K sub 22 e to the lambda 1t, and then you'd keep going in this fashion until you got to capital X m equal to capital K m1 times t raised to the m minus 1 over m minus 1 factorial times e to the lambda 1t, and then plus capital K sub m2 t raised to the m minus 2 over m minus 2 factorial e to the lambda 1t, and then you'd keep going until you got to capital K, so those are eigenvectors, sub mm e to the lambda 1t, where K sub ij, our column vectors, can always be found. Cool. So it looks complicated, but it's not hugely complicated. All right. So let's check it out. Eigenvalue of multiplicity 2. So find the general solution of this given system. So let's check it out. So remember, it's useful to have your A handy. So in this case, A is 3, 2, 4, 2, 0, 2, sorry, and 4, 2, 3. And then we need A minus lambda I, so it'll just be 3 minus lambda, 2, 4, 2 negative lambda, 2, 4, 2, 3 minus lambda. And of course we're using I3 because we have A is 3 by 3. And I3 is the identity element for multiplication, matrix multiplication for 3 by 3 matrices. Groovy? Okay, so step 1, we want to find eigenvalues. So, setting up our characteristic equation, remember we want the determinant of A minus lambda I. So 3 minus lambda, 2, 4, 2 negative lambda 2, 4, 2, 3 minus lambda, and that is set equal to 0. So this one, it'll be a little bit of a pain. We need to get the, we'll go ahead and expand about that first row, and then the trick to find the sign of the cofactor. And we will have, so we'll have 3 minus lambda is positive times the determinant. When we cross out the row and column 3 minus lambda is in, we're left with this 2 by 2 determinant. So we'll have negative lambda 2, 2, and then 3 minus lambda. And then minus 2 times, now this time you'll be crossing those out, and you're left with the other things there, 2, 2, 4, 3 minus lambda. And then plus 4 times the determinant, 2 negative lambda, 4, 2. And that's all equal to 0. So we will have 3 minus lambda times negative lambda times 3 minus lambda. So remember, we multiply that main diagonal, and then we subtract the product of the other diagonal to find the 2 by 2 determinant. And then minus 2 times 3 minus lambda, minus 8, multiplying across, plus 4 times 2, minus negative lambda times 4. All right, and then that's equal to 0. Don't forget about that. So we will have 3 minus lambda times negative 3 lambda plus lambda squared minus 4. minus 2 times 6 minus 2 lambda minus 8 plus 4 times 4 plus 4 lambda. All of that is equal to 0. And then we'll get, we can multiply this through now. So we'll get negative 9 lambda plus 3 lambda squared minus 12 plus 3 lambda squared again minus lambda cubed and then plus 4 lambda. So all of this is all of this. And then we will have, let's see, 6 minus 8 is negative 2. So we'll have plus 4 and then plus 4 lambda. And that's this one. And then we will have plus 16 plus 16 lambda is equal to 0. All right, so now combining everything, I think we only had 1 lambda cubed, so negative lambda cubed, this guy. And then we have a 3 lambda squared, another 3 lambda squared. So we'll get plus 6 lambda squared. And then, let's see, we have negative 9 lambdas, 13 lambdas, 17 lambdas, or no, sorry, negative 9 lambda, negative 5 lambda, negative 1 lambda, and positive 15 lambda. And then negative 12 plus 4 is negative 8, plus 16 is positive 8, and all of that is equal to 0. Now for this one, if we just go to our y equals, let me clear some of these things out. Actually, we're going to quit out of here. We're going to go into mode, function, done, y equals. So I'll have clear, clear, clear. There we go. And we'll have to put x's in just because of this calculator. So negative x cubed plus 6x squared plus 15x plus 8. And then if we graph that, we have there we go. So here, if we, it looks like it's going to be at about 1. So let's go ahead and click on the graph, and we're going to calculate the right of that second 0 is 10. And it looks like we get a 0 at 8. Okay, so we'd have lambda 1 equals 8. Let's go ahead and calculate that, push that down. That one crosses the x-axis, so it has a multiplicity of 1. This one over here is tangent to the x-axis, so when we go to calculate 0 for this one, it'll have a multiplicity of 2. Okay. That's another way we can do it. We can look at what the 0 is right there. And we're right on the 0. Go to calculate. And value x is -1, y is 0. Perfect. So this one for lambda 2, it's -1, and it's got a multiplicity of 2. So we'll swing that one back. And now our next step is to find the eigenvector. And there'll be multiple eigenvectors. Okay, so with the eigenvectors, remember that you're looking at A minus lambda I times K, the vector K, equals to the 0 vector. So we'll call it K1. All right, and so actually, you know what? I'll just say K, and then we'll go to a different color and find K1. So our first one is lambda 1 is 8. So we're going to be looking at A minus 8I times K1 is equal to the 0 vector, making sure I have lots of space. And so remembering we found A minus lambda I, so it'll be 3 minus 8, which is -5, and then 2, 4, 2, and then negative lambda, so it'll just be -8, 2, 4, 2, and then 3 minus lambda, we get -5 again. Cool, cool? So our K's, well, entries are K1, K2, and K3, because it's a 3 by 3 coefficient matrix, and that's all going to be equal to 0. Cool, cool? And then how do we solve that? Well, we make the augmented matrix. And then we find the reduced row echelon form using our technology. So we'll finish off there. Go to matrices, and then I'm going to edit matrix C, and we'll have a 3 by 4, and let's see, -5, 2, 4, 0, 2, -8, 2, 0, and then 4, 2, -5, and 0. Quit out of there. And then we'll go to second matrix math, and we want our REF, and then back to second matrix C, and magic. We will have 1, 0, -1, 0, 0, 1, -1/2, 0, and then the last row zeroes out. And so we will have the following: K1 minus K2, K3, sorry, is 0, which means that K1 equals K3, and then K2 minus 1/2 K3 equals 0. So that gives us K2 is equal to 1/2 times entry K3. So now we're going to get, so if we let K3 equal to 2, then K1 equals 2 and K2, this is why I let K3 equal 2 to 2 is 1. So capital K1 will be the column vector 2, 1, 2. Groovy? All right, so now we will take a look at lambda 1, 2 equal to -1. So we're going to be looking at A minus -1 times I times capital K2 equal to the 0 vector. All right? When we go through and we plug in -1 for lambda, right, we'll have, it'll turn everything positive, so we'll end up getting 4, 2, 4, 2, 1, 2, and then 4, 2, 4, and again times K1, K2, K3 equals 0, 0, 0. So setting up the augmented matrix and using our technology, we will have so I'm going to go back to matrices, and then I'm going to edit matrix C because it'll be pretty similar. The only things that'll change will be the main diagonal and then here's a trick. You can go second enter to get to entry, and it gets all that REF stuff done for us. So we'll have 1, 1/2, 1, and 0. And then we have 2 rows zeroing out. So let's see what we've got going on. That means that K1 plus 1/2 times K2 plus K3 is equal to 0. So we're going to have to choose, we're gonna end up getting, we have 2 parameters here, so we'll be able to get 2 eigenvalues out of this. So for K1, let's see what we'll do. We'll have K1 is equal to -1/2 times K2 minus K3. So if I let K2 equal to -2, that would give me a +1, and I'll let K3 equal to 1. That'll mean that K1 is 0. So we'll get our first vector will be capital K, and this will be actually vector K2 will equal to 0, negative 2, 1. Now, we're going to use the same basis, okay? Or not base, I don't want to say basis. But we still have the same situation. We still have K1 is equal to negative 1/2 K2 minus K3. So now we just pick different values for these, all right, to get vector K3. So if we let K2 could equal to negative 2 again. And I'll just let K3 equal to 0. And if that happens, then K1 will equal to 1. So the other eigenvector will be 1, negative 2, 0. Cool, cool? All right, so now the solution, right? So here we go. So to find our general solution, we will have our x solution vector will be the linear combinations of solutions. So we will have C1, and that was all the purple stuff where lambda was 8, is going to be 2, 1, 2 times e to the 8t plus C2, that's going to be our K2 vector, 0, negative 2, 1. That will be times e to the negative t, because lambda is negative 1, and then plus C3 times 1, negative 2, 0. See if I can move this over a little. Times e to the negative t. Groovy? And that's it. That's our solution. And so sometimes we need to get a second solution, all right? So now suppose that lambda 1 is an eigenvalue of multiplicity 2, and there's only one eigenvector associated with this value. So here we were able to pick two different values, right, or different values, because we had two parameters here, K2 and K3 could be parameterized as S and T. And so we were able to get two eigenvectors out of it. But what if you can only get one eigenvector associated with that value? It turns out a second solution can be found of the form capital X2 equals capital K times T e to the lambda 1t plus capital P times e to the lambda 1t, where capital K equals K1, K2, like the normal stuff we do to find the eigenvector, and P is P1, P2, all the way down to Pn, but there's a little bit of a trick here. It turns out that, so the way you get K is the normal way, right? So you'd have A minus lambda 1 times I times capital K equals the 0 vector. But the way you would get P is you would say A minus lambda I times P, that P vector, is equal to the K vector instead of the 0 vector. All right, so now let's take a look at an example. All right, so find the general solution of the given system. So A is equal to 12, negative 9, 4, 0. And so A minus lambda I is equal to 12 minus lambda, negative 9, 4, and then negative lambda. And again, we're using I2 because A is 2 by 2. So this is the I we were using. And now let's go ahead and go to step 1, which is to find eigenvalues. So we're going to have, remember we're finding the determinant of A minus lambda I and setting it equal to 0. So that's going to be the determinant of 12 minus lambda, negative 9, 4, and negative lambda. Set that equal to 0. So we'll have 12 minus lambda times negative lambda minus negative 9 times 4 equal to 0. That's going to give us lambda squared minus 12 lambda plus 36 is 0. And if we factor that, we'll have lambda minus 6. The quantity squared is equal to 0. So lambda 1 is equal to 6 with multiplicity 2. So now let's go ahead and, go to step 2. Find eigenvectors. So we've got our lambda 1 equal to 6. So we're looking at A minus 6I times capital K to get our first eigenvector equal to the 0 vector. So then we will have (12 minus 6 is 6). Then we'll have negative 9, 4, negative 6 times K1, K2 equals 0, 0. And then putting it in the augmented form, we'll find the reduced row echelon form. And let's go to our matrices. And we'll edit B. And we will have 6, negative 9, 0, and then 4, negative 6, and 0. We'll quit out of there. And second matrix, math, RREF, second matrix, B. And that'll give us 1, negative 3/2, 0, and then 0, 0, 0. So when I go back and check this out, I have my K1 minus 3/2 times K2 is 0, which gives me that K1 is equal to 3/2 K2, but I don't have some other parameter, right, to make two vectors out of. So I'm going to have to use that other way. But I certainly can get my capital K vector. So we can let K2 be equal to, I don't know, whatever you want it to be. Why don't we let it be equal to 2? So then K1 will equal to 3. So our K vector will be 3, 2. And then now going into the next one, so we need to use that other way. So we're going to have lambda, nope, not lambda, my bad, a minus 6i, because 6 is lambda, times that p vector is equal to our k vector. So what does that look like? Well, we'll have the same coefficient one, so 6, negative 9, 4, negative 6, times P1, P2 equals to our K vector, which is 3, 2. So setting up our augmented vector, or augmented system, augmented matrix. Instead of doing zeros at the end, we have our 3 and our 2. And our REF of that will give us, so coming back, this one will be faster. We'll still go back to that matrix B. So we'll edit matrix B, and this time it'll just change that last column to be 3 and 2. Quitting out of there, we can now go to second entry, and we get 1, negative 3 halves, 1 half, and then 0, 0, 0. Isn't that cool? So that's going to give us P1 minus 3 halves P2 is equal to 1 half which gives us that P1 is equal to 3 halves P2 plus 1 half. So we might as well let P2, really whatever you want it to be, but we could let P2 equal to 0, and that means that P1 would just be 1 half. And so our vector, capital P, would be 1 half 0. And so now for our solution, so step 3, our general solution. Coming back here, we'll have that second part of the solution is going to be all of this, okay? So let's see what we get. We will have capital X equals, well, we have C1 times our first vector, K, 3, 2, times e to the, 6t. Now, plus C2 times the quantity. So we'll have the vector K, 3, 2, times T e to the 6t plus our vector p, which was 1/2 0 e to the 6t. And that is our general solution. Groovy? All right, I hope you have a wonderful morning, afternoon, or evening whenever you're watching this show. And hey, if you like what I'm doing, hit that subscribe button and like my video, please. Bye.